If we start from the Metropolis-Hastings algorithm, which was the algorithm to implement MC methods that we saw in the previous videos. And what this said was that I had a proposal distribution G, which is suggesting states which my Markov chain might move to. And I would compare the likelihood of the proposed move to the likelihood of my current move in my target distribution, in the thing I'm trying to sample from, and I'd calculate this acceptance probability. And what this would mean is sometimes when the proposal distribution suggested you're in state 3, I think you should go to state 10. Sometimes my chain will say, yes, I'll do that. Other times it will reject that move and stay where we are. And that's based on this acceptance probability. Now, the real strength of this, and the reason that it's become such a major bit of the statistical toolkit in the last, I suppose, century, half century maybe, is that we don't actually need to know the target distribution explicitly, this pi distribution. All I need to do is it relies on the ratio pi of my proposed point xp divided by pi of my current point, pi of x. So I don't actually need to know the distribution. I don't need to know those values. I just need to know the ratio of them. So it doesn't mean that there's ever any difficult to calculate normalizing constants. I can ignore it on the top, and I can ignore it on the bottom, safe in the knowledge that whatever factor I'm wrong by in calculating the top, I'm wrong by the same factor in calculating the bottom, and so the ratio will still be correct. And this actually plays very nicely with some Bayesian statistics and Bayesian inference, because very often the hardest part of some of these Bayesian derivations would actually be to calculate those normalizing constants. Now that's true in many cases, but particularly as we start to get up to the complexity of models that people want to fit using MC type approaches, it's an unbelievably big advantage. If I've got 20 parameters I need to sum out or integrate out over my uncertainties in, I don't want to be doing many 20-dimensional integrals anytime soon, and I'm sure you don't either. We will just now briefly introduce the idea of Bayesian statistics and Bayesian inference. And it's really, I suppose, a philosophy of interpreting statistics and chance and probability. And it's built on Bayes' theorem. And it's really this idea of saying, which range of values do I believe this parameter lies in? If I've got something I want to know, some quantity I want to know, I might say, well, my best guess is a given value, but I could believe values in a given range with given credibility, given credence. And I want to update that as I get more evidence, because clearly if I believe something, but all of my evidence is suggesting that I'm wrong, maybe I should update my belief to be more influenced by the evidence. For those of you who haven't met me, that's a video of me flipping a coin. So let's say we've got this coin and the parameter theta describes the probability that the coin will land heads on a given flip. So what I'll do is I will record a sequence of outcomes. I will flip this coin repeatedly and I will record whether the coin lands heads or not. What I want to do in a Bayesian framework is to start with a prior distribution. And the notation here and the names here make a lot of sense. This pi of theta depends only on theta. There's no x's, there's no evidence in this at this point. This is what do I think prior to getting any more evidence. So maybe I'll say, I think the coin's fair. So if I start by thinking that theta will be about 50%, I don't know it's going to be exactly. If somebody told me that coin was not 50% heads, but was in fact 49.9% heads, I'd believe that nearly as much. Maybe a bit less likely than 50-50, but it still seems believable to me. If somebody told me this coin had been made so it was 40% heads, 60% tails on each flip, I'd be skeptical. I wouldn't say it's impossible, but I'd have a lot more doubt about that. If somebody told me this coin was 99% chance of landing heads on a flip, without any evidence, I wouldn't rule that out, but I'd be very, very, very skeptical. So I'd start with a prior distribution that's sort of describing the range of values which I believe are possible and the relative chance, the relative credence or credibility I give those. And so what I want to do is I want to gather a set of observations for whether this coin landed heads or tails, and I want to use my new observations potentially to change my mind. And one of two things should happen when I get new evidence. Either I start to think my prior distribution is wrong, and then my evidence makes me change my mind, or I start to think that my prior distribution was in the right place, was thinking the right thing, in which case it should strengthen my belief or my certainty around that, what may be a guess. If we start with a prior distribution, returning to a little bit of likelihood theory, we can also calculate the likelihood of seeing the evidence we did, the set of outcomes, the heads and tails in this case, if I knew theta. I don't know theta, I can guess theta, but I can write down the likelihood of the evidence given the parameter, which in truth I don't actually know. So this likelihood is a function of the parameter, which I don't know. And then Bayes' theorem is just this way of inverting these conditional probabilities. So if I rearrange this, what I actually get to is I can get to f of theta given x. And so what this is saying, what do I think about the parameter now? What do I think about theta now, given the evidence? And it's this product of f of x given theta, which is the likelihood of my observations given theta, which in fact I don't know, times my prior belief, f theta. But the point is, I need to normalize that to get the true statement for the posterior. And the posterior, again, the notation and the name make a lot of sense. F of theta given x. What do I think about theta given a set of observations x? And this is post the experiment, after I have more data. So the posterior density is equal to the prior times the likelihood divided by integrating out over the uncertainties, and that can be the hard part. It's also why we sometimes say the posterior is proportional to the prior times the likelihood. And if I'm fitting with something like Metropolis Hastings, I don't even care about that denominator because it will cancel out when I work out the ratio of posterior probabilities.